afternoon, everybody. Um, so we're going to focus in on soils for a little bit. And primarily we'll talk about what makes up soil, soil composition, soil properties, and then how we help to maintain soil quality. All right. So what we have here is a photo of something you guys ought to be familiar with. It looks a little bit like a succession pattern. Notice that we're starting with rock fragments, our parent material. It's what we call a bedrock. So we're going to label that parent material. Okay. And the bedrock weathers and erodes over time. Moss and lichen actually help that process along. Over time, the mineral particles that come from that parent material have other parts added to them, like organic material, organic debris as things grow. Then we end up with a layer of topsoil with these various soil horizons that we'll get to a little bit later in this lecture. All right, so soil is a mixture of mineral particles that come from the parent material and organic material from living organisms that grow in the soil and then die and decompose. So the composition of soil, like I said, is mineral particles from that parent material, organic material, so leaf litter, animal dung, dead remains of plants and animals, right? That organic material that forms near the surface of the soil creates what we call humus. Okay, not to be mistaken with hummus, a yummy Mediterranean food, right? Humus is that really dark, almost black uh, type of soil that's really, really rich in dead and decaying organic material. All right. And then, of course, our soil is going to have pore spaces. And in those pore spaces, we're going to find water in that soil and air in that soil. Both are important components. So we're going to talk a little bit about the size of the particles that make up the soil and how the size of those particles determines some really important properties about the soil. All right, so some general relationships that I want you to remember. When we increase our particle size, our porosity actually decreases. Even though their pore spaces are larger, when their particles are very small, there's a lot more pore spaces. All right. Now, the other important characteristic I want you to remember is that as we increase particle size, permeability increases, which means even though there are fewer pore spaces with larger particles, the pore spaces that are there are larger and better connected to each other. So it's much easier for water to flow through soil that has larger particles than it is for it to move through soil that is composed of primarily smaller particles. I apologize for fumbling over my language there. So, soils with small mineral particles are less prone to leaching. All right, so leaching is an important term. And basically, as water dissolves materials and percolates through the soil, right, leaching is the loss of water soluble nutrients. Okay, so when we have small mineral particles, we are less prone to losing those nutrients because the permeability of those small particles is low. So water is not as easily able to work its way through the soil, dissolve nutrients, and essentially wash them away. So smaller particles tend to have a higher level of nutrients. All right. So, we're going to talk a little bit about soil properties and particle sizes. And what I want you guys to remember is the impacts of things like clay, silt, and sand on the properties of a soil, right? So, soil texture affects its properties. So, texture is essentially referring to the amount of clay versus silt versus sand, or essentially the particle sizes or the mixture of particle sizes. right? So if we have a coarse textured or sandy soil, it will not hold water well, because again, we have bigger particles, better connected pore spaces, highly permeable, which means more prone to leaching, right? So coarse textured soil will not hold water well. Fine textured soil, so soils that would have a high amount of clay, right, would have very poor drainage. So even though there's a lot more of those small particles and actually a higher porosity, water is much less able to percolate or permeate that type of soil. So because of that, tend to have poor drainage, low oxygen levels, right? But because water does not flow through them very well, they tend to be high in plant nutrients. Okay, so again, some important things to remember. Coarse textured soils, high permeability, and because of that, very low nutrient content. Fine textured soils that are high in things like clay, right, have very poor drainage and permeability, but also relatively high nutrient content, right? So on one hand, we get great drainage, but poor nutrients. On the other hand, we get really poor drainage, but high nutrients. All right. So just to basically help you guys understand, not only is it because water doesn't flow through very well, but clay tends to have a negative charge on its surface, which attracts a lot of important ions like magnesium and potassium and calcium, ammonium, other important ions that are important to plants. All right. So we will do an activity. This is going to be something I'm going to try to have you guys do at home. But we'll do an activity that allows you to examine the soil composition or the texture of your soil. And basically, a brief description of that process is you would take a sample of soil, add some water, just enough to fully saturate the soil and allow it to get suspended in the water, and then let that soil settle out over time, right? And what will happen is the first material to settle out will be the larger particle sizes. So the sand, on top of that would be the silt, the medium particle sizes, and then on top of that would be the clay. And then what you can do is you can measure the height of each layer to determine what percent of that soil is sand, what percent is silt, what percent is clay. And then you can connect those percentages um, to determine where you fall on this soil triangle. So we will do some activities with this soil triangle later. But let's say, for example, we have 60% silt, all right, 20% sand, and 20% clay, right? What we do then, right, is I'm going to draw a line here for my 60% silt, going to draw a line here for my 20% sand, and then a line here for my 20% clay. Where those intersect tell me what type of soil I have, which would be what they call a silt loam. So it'll be a little heavy on the silt, but generally speaking, if we're looking for a high quality agricultural soil, so something that's good for growing things like food, we'd look for something in this loam range. Okay. Now, loam is important because it's got a good mixture of particle sizes. We have some clay, which helps the soil hold on to nutrients. We have some sand, which helps with permeability, but primarily we're composed of silt, which is sort of a mixture because it's in between particle sizes. It kind of has a mixture of properties. It does allow drainage, but not too quickly. It does hold on to uh, nutrients as well, but it doesn't get waterlogged or prevent water from draining out like clay does. So if you want to grow some good food, right, you'd be looking for something that is within the range of some sort of loam or type of loam soil. All right. So there's a pretty good table here from my old textbook, actually, but just talking about the different soil texture types, all right, and how they fall into like aeration, which would be how much air could be in the soil, how well it drains, how well it holds on to mineral capacity. And notice that loam doesn't hit the high on either drainage nor nutrient capacity. It kind of fits in the middle because it's primarily composed of silt. So you get sort of a little bit of both worlds in that case. All right. Now we're going to talk briefly about what we call soil horizon. So if you could essentially take a core sample of a soil, right, or go to a hillside and just that hasn't been washed away or weathered too much, just sort of dig straight down, uh, what you'll run into is sometimes very obvious changes in the composition of the soil as you go down, right? So the O horizon, the O really, you can remember that as our organic, right? That's going to be where we have loose and partly decayed organic material. And this is where we would find our humus again, okay? Beneath that O horizon, which can vary in thickness, is our A horizon. That's what we would refer to as our topsoil, all right? So it's primarily mineral matter, but it does have some organic material mixed in with it. Beneath that is what they call the E horizon, right? And that would be similar to our topsoil, but it's heavily leached, right? So very low nutrient capacity in that layer right there. And then beneath that is the B horizon, which is where we tend to get our clay accumulating. All right. So it can actually be fairly high in nutrients, mineral nutrients, anyways. But it doesn't have the types of properties we'd look for in a high quality soil. All right. And then our C horizon is where we start getting close to the bedrock, where we have large pieces of rock and gravel mixed in with soil. All right. So you guys are going to want to know what those soil horizons are and their basic properties, but don't spend too much time on it. Um, so there are lots of different soil quality tests that you can do, and I'm just going to run you guys through them. Many of these, hopefully, we'll get an opportunity to do in the lab, depending on whether we are still distance learning when you're watching this. But um, for soil properties, one of the things you can measure is soil acidity or the pH of that soil. Now, the reason that's important is that the pH impacts which nutrients are soluble. All right. So what you do is maybe make a water and soil slurry, right? And just put a pH probe in there and get a quick measurement of the pH. Typically, we're looking for something near neutral. That's when most of our important nutrients are soluble. Although some plants prefer more acidic soils, others prefer more basic. So it kind of depends on what you're trying to grow as to what the optimal pH is, but most plants tolerate a neutral pH pretty darn well. All right. Um, so soils can range from 4 to 8, right? And like I said, it affects the solubility of certain nutrients, but typically we look for something very near that neutral mark, right? Maybe slightly acidic. Not too many plants really prefer the alkaline or basic soils. Uh, but again, different plants are adapted to different ranges in those pH. But optimal, what we would look for, particularly in agricultural soils, like maybe a pH of 6 or 7, very close to neutral. All right. Other properties, things we can test with regard to soil is physical and chemical tests. So physical tests would be checking for soil texture, like we just talked about, right? What percent sand, what percent silt, what percent clay do we have? Those are important things because they give us an idea of how porous it is, uh, how well we're going to hold on to the moisture that's in there. Is it going to leach easily? Is water going to drain through too quickly, those kinds of things. And then chemical tests would be, again, like a pH test, testing for specific minerals. So we want to look at, well, how much nitrogen is in the soil? How much phosphorus is in the soil? You can test for specific nutrients. Those would be chemical tests. Another test you could do is an organic content test, where basically you take the mass of the dry soil before, you heat it up to burn off any organic content. Um, you take the mass after, right? And then you can determine what percent of that soil is organic content. Um, let's see. Well, we're gonna skip over this. We're getting a little bit long-winded. All right. Um, so when we talk about the quality of soil, right, we also want to recognize that soil is a renewable resource. And soil can be used in both sustainable and unsustainable ways, much like many of our other resources. Okay, so in the case of this picture, what we're looking at right here, so this is the Gobi Desert, by the way. Okay, the Gobi Desert's in China, right? Um, Now, one of the things that was occurring in China as population grew and it became more and more heavily cultivated for agriculture is they noticed that the Gobi Desert seemed to be encroaching or increasing its size. So more and more land was going from productive farmland to unproductive desert, right? So the biocapacity, like we talked about in the ecological footprint area, was decreasing. All right, due to the way they were treating the soil in places. And so one of the things they did, and this is what we're seeing in this picture. I mean, we're going here's the desert, here's productive farmland, right? What they did to help prevent this desertification is what we call that, is you'll notice right along the fringe of that Gobi Desert, they planted a ton of trees. And in fact, they actually call this the Great Green Wall, right? And so simply planting trees, right, with extensive root systems to hold that soil in place halted the encroaching desertification that was occurring, maintain soil quality, and we are able to prevent this process by which we go from highly productive agricultural land to not productive desert. So planting those trees held the soil in place, prevented that soil erosion, right? And that's what they called the Great Green Wall. It stopped the encroaching of that desert in that area. All right. That takes us to some really important points. Soil is a resource. It's renewable, yes, but it does need to be managed. And there's best practices that farmers and ranchers can employ to help maintain their soil quality. Right. So, a really important case in point here. So, those of you who've had U.S. history, you're probably familiar with the Great American Dust Bowl. Right. So, the plains are grasslands, which typically have very high quality soils. Um, right? They are subject to periodic droughts, some more severe than others. All right. So between 1930 and 1937, just leading right up to World War II there, during the Great Depression, they were experiencing a very severe drought. Now, grasslands are adapted to that, right? And even though the grass that you see above the ground might look dry and dead, those root systems go dormant and can survive really, really long periods of drought. Um, and then as soon as the rains come back, those grasses will essentially send new grass shoots up, and we still have a healthy, productive grassland ecosystem. Now, in the case of the Dust Bowl, right, they removed a lot of that native vegetation and grasses for agriculture. All right, so our root system that held the soil in place in our grasslands, sod is how we refer to that as, was removed to clear land and plow for planting annual crops for agriculture. All right, now because of the severe drought, those crops failed. All right, and because the crops failed, there were and no their grasses had been removed. There was nothing to hold that soil in place. Uh, and so, with the severe drought and dry conditions and winds, all of that healthy topsoil was essentially blown away, right? And that's what created that Dust Bowl conditions. Yes, there was a drought, um, but right, had the native vegetation been left in place, the grass has been left in place, the grasslands would have survived, and that drought would not have been nearly as catastrophic on the ecosystem as it was. All right. And a lot of it really just came down to poor soil management. Um, Not to the fault of those folks back then. They just didn't know how to manage soil properly at that time, but they learned a lot from this. All right. Um, so some other really important soil problems, what we call nutrient mineral depletion, right? So, and this is again a really important part of agriculture. So we learned back in Unit 1 about these really important cycles, right? Plants uptake things like nitrogen and phosphorus, right? Assimilate them into their tissues, and when they die and decompose, they return those nitrogen and phosphorus back into the soil. They can be taken up again by new plants, and we get this nice ongoing cycle. Now, in the case of agriculture, what happens is we grow something like tomatoes, like you're seeing here. So those plants uptake really important nutrients, and rather than letting those plants die and return those nutrients, we harvest things like tomatoes, remove those plants, and so all the nutrients that went into the tomato plant are removed from that system. And over time, the nutrients taken up by the tomatoes begin to deplete. And so we have run into what's called a nutrient mineral depletion. The way farmers get around that is to re-add those nutrients through things like fertilizer and things like that. All right. Another really important soil problem in our more arid areas is soil salinization, right? So essentially what you're seeing here, that white material on top of the soil is salt. All right. Um, and so soil salinization is the gradual accumulation of salt in the soil, usually due to improper irrigation techniques. So, for example, if you water an area that's really arid um, and that water evaporates, even though it's fresh water, it does contain trace amounts of salt in it. The water evaporates and the salt's left behind. If carried on over and over and over again with poor irrigation techniques, those salts build up in the soil that they become toxic, and plants can no longer grow there. All right. Now, the last one we do want to talk about is what's called desertification, right? Not to be confused with desertification, which would be delicious. Desertification is referring to that process I talked about back with the Gobi Desert example. Desertification occurs when you take a productive, semi-arid ecosystem and through poor soil management, it essentially becomes a desert. All right. It's typically a human-induced condition because in those semi-arid areas, remember we have vegetation that is adapted to periodic droughts. They go dormant and hold on until the rains return. All right. So through poor soil management, right, we get this process of desertification, um, which can obviously impact vegetation, but it actually has climatic implications that are important as well. All right. So we do have some soil conservation policies in the US. A lot of them are a result of what we learned back in the Great American Dust Bowl. All right. So in 1935, they authorized the formation of the Soil Conservation Service. Um, and basically, they designed best practices for farmers to use to help prevent soil erosion. So, in the case of droughts, we don't run into these severe dust bowl conditions again. Because we've actually had droughts just as severe as what occurred in the 1930s, because we understand how to water and irrigate much better, and we understand soil management much better. We didn't have anywhere near the level of harshness of a condition as we had back then. All right. Um, and through the Food Security Act, they actually created what's called the Conservation Reserve Program. And some of you might be familiar with what they call CRP land. So CRP land is basically highly erodible land that the government says, you know what, let's not farm that because if conditions change, soil is going to erode very quickly, right? Much more quickly than we can regenerate our soil. So they actually will pay farmers not to farm portions of their land to help maintain soil quality, right? And that's called CRP land. So in the case here, you can see cornfield, right? But they're actually having the farmer leave that with native vegetation in place. All right, I got pretty long-winded there, so I'm going to end it right there.